Okay, guys, the second video of 1.2. I want to look at number 48 in the book. And we have another rational equation, as you can see, and there's a little more going on. Now I have some variables in that denominator. Now, this gives us sort of an extra step from before. When we talk about LCDs, we always want everything in the bottom fully multiplied, okay? Or sorry, fully factored. Wrong wording. Okay. The reason we want fully factored is because when we look for LCDs, right, we're always looking for the smallest number that they all go into, that they multiply into. Okay. So can I somehow write x squared minus 25 as something times something else? X plus 5 is fully factored, x minus 5 is fully factored, but x squared minus 25 is not. That's a difference of squares. So first step, when you have something like this, you want to get the bottom fully factored. So that's what I'm going to do here. Okay, so I have 4 over x plus 5, that's fully factored on the bottom, plus 2 over x minus 5 is equal to 32. Now x squared minus 25, hopefully your factoring is up to snuff. As a difference of squares, that's x plus 5 times x minus 5. So I've just rewritten the problem. Okay, well, why did I do that? Well, that helps me find the LCD so I can once again get rid of the fractions. So question is, what is my LCD? Well, let's look at what I have. I want the smallest thing that x plus 5, x minus 5, and x plus 5 times x minus 5 go into. Essentially what you're saying is you want something that basically sort of takes into account each of these factors, okay? So I need an x plus 5, okay? That took care of this one and this one. These are accounted for, but I also have these x minus 5, so I have to include that in my LCD. That is my LCD, x plus 5 times x minus 5. I've now accounted for the x minus 5s, okay? I know it's the same as x squared minus 25 right here, but there's a reason we want it factored. If you remember, the strategy is we're going to multiply both sides. This is how I'm going to indicate that since I'm a little low on room, by that LCD, x plus 5, x minus 5. And once again, I like to write it over 1. And remember, I'm going to have to distribute that to each term in here, right? Okay. So when I do that, okay, and you can skip some of the steps as you go, as you get a little quicker, but I'm going to write them all out right now. 4 times x plus 5, x minus 5. Notice that's that top distribution right here, all over x plus 5 times 1, okay? And you can probably already see sort of what's going on here, okay? Plus 2, well, you got to distribute this again, x plus 5, x minus 5, all over x minus 5. Once again, you might be able to see what's going to happen. This sort of makes it a little more obvious to see, right? And finally, that's equal to 32 times x plus 5, x minus 5. Sorry, I got a little bit of a shadow there. I think you can see, though. Over x plus 5, x minus 5. And here's the cool part. Very satisfying, right? This reduces to 1 over 1. That reduces to 1 over 1. And these all reduce. So literally what we end up with, something that looks a lot nicer, is this. 4 times x minus 5 plus 2 times x plus 5, that's all I got left on the left-hand side, is equal to simply 32. And once again, it's a nice linear equation now, okay? So I distribute right there and right here, and that's equal to 32. Okay, I want to combine any like terms. I got 4x, I got 2x, that's 6 x's, taking into account these guys. Minus 20 plus 10, that's minus 10, equals 32. So I have 6x minus 10 equals 32. I'll go ahead, I'll add 10 to both sides, add 10, and I'm getting 6x equals 42. And finally, I want to go through, divide both sides by 6 to get x by itself, okay? So I'm seeing that x is equal to 7 in this case, okay? And you can write your answer like this, or sometimes we write it, especially when we have multiple answers, in set notation. So either way is fine, Okay. Now, one thing you want to make sure when you get your answers, you always have to check that if you were to plug it back into the very original, so if I took 7 and I plugged it in right into here for all the x's, you have to make sure that it wouldn't cause division by 0. For example, if I got x equal to 5 as an answer here, that would cause a problem here, and it would also cause a problem here. It would cause the denominators to be 0. So do always check that. If that happens, you have to throw that answer out, and my answer would be no solution in this case. So do watch for that. Okay, let's move on. There's 2 examples that I kind of picked out myself, and I want to just solve these. They're simple linear equations, and I just want to see if something interesting happens. You can probably guess it is going to. I'll do my distributions. I go through and I see I got 2 plus 3x minus 12 is equal to 3x minus 10. And you might already see something is a little fishy. Okay. Combine some like terms. I got a positive 2 and a negative 12. So I guess that's a negative 10. And now you're probably really noticing something's kind of interesting. If I try to get my x's on the same side, something weird happens, and I end up here. What the heck does that mean? Yes, I know negative 10 equals negative 10. My x's disappeared. What the heck is x? When this happens, when you just get a true solution, it turns out you can see each expression on the left-hand side and the right-hand side, they're actually the same expression. They're just written differently. So it doesn't matter what you put in for x. So usually I call this infinite solutions, okay? Which you can also call an identity. Those are the 2 ways you can refer to this situation. Okay, so that's kind of an interesting one. And down here, likewise, let me combine a few like terms. I have 8 minus 4x on the left-hand side. And the right-hand side, if I distribute, okay, so I'll go right here. And I just realized this plus 5 is supposed to be out here, so I'll just get rid of that. 4x plus 5. Okay, so we have this. Combine any like terms. 8 minus 4x equals, I guess that's 13 minus 4x. Once again, something interesting is happening. I add 4x to both sides, and once again, my x's are going away. But it's kind of a really weird situation because I'm ending up here now. And 8 is not equal to 13. So what the heck happened? Did math fail us? What's going on? Well, it turns out that this doesn't have a solution. It has the same amount of x's, but different constants on each side. In a case like this where the x's disappear and you only end up with some untrue statement, we say that there is no solution, which is also known as a contradiction. I'm okay. You can use either terminology. Both of these are fine. And that does it for section 2, guys.